Okay, everyone's back. So again, what we're trying to do is really just focus in on interpreting our models. So hopefully this example we've done right now, looking at the STR, or student-teacher ratios relative to testing scores, is kind of helping visually let you see what the regression is doing and interpret the coefficients in a slightly better way rather than just numbers, right? Let me see if I can share my screen now. Looks like it's working. Okay, so again, this was the model we estimated. We walked through before our little break, taking the partial derivative with respect to the student-to-teacher ratio. We said we can multiply the denominator, the change in the student-to-teacher ratio across both sides, and that gets us down to this equation here. The change in the total score is equal to minus 4.5596 times the change in the student-to-teacher ratio. So as the student-to-teacher ratio increases, and again, the domain for this is from 0 to infinity, right? It's going to be most well-behaved where we actually have data, or the domain where we actually have data for. So as the student-teacher ratio increases, for each unit it increases. So every additional student per teacher is going to correspond to a decrease in the test scores of minus 4.5 points, right? And Francis pointed out to us right before the break that, well, sure, that's what our data is telling us, or that's what this one model is telling us with one explanatory variable. But there's another school of thought, which is, well, having more people in the classroom can facilitate more ideas to flow. If someone's shy, someone else can ask a question. So it's really not entirely clear. I mean, here we're getting one result, but logically you can argue the other way, right? Okay, so that could be pointing that maybe our effect is too big, maybe our effect is wrong, maybe our model is misspecified. Nonetheless, that's what our first pass or our first regression is telling us. Okay, so this was one specification. Again, we have student-to-teacher ratio as units, so it's like people to people. And our y variable is test score, so points. That's only one way of specifying the model. We can re-specify the model to ask a slightly different question. Rather than saying, how does the test score change as the number of people, that is the students to teachers, changes, wouldn't it be easier if we just had something like percentages? So like if the student to teacher ratio increases by 10%, what's going to happen to the test scores? Make sense? So whenever you're specifying your model, you can actually fiddle with the way the variable enters into the equation. And depending on how you manipulate the variable going in, it actually have really profound effects on how you interpret the model. Okay, so if we wanted to implement this idea of trying to track percent changes in the student to teacher ratio, so that is, if a school is looking to implement some new measures in order to reduce the student to teacher ratio, okay, so that is, they start sending some kids home. It's like, no, you're not going to educate you anymore. No one likes my joke. Okay, we're kicking some people out. The student to teacher ratio then starts to decline. And let's say we're going to do this for 10%. The way we can actually implement this, we don't need any additional data. We can literally take the existing data we have, we can just reformat it. Specifically, if we take the natural logarithm of the student to teacher ratio, the interpretation of the regression is now going to be in percentages. Okay, the reason for that is basically has to do with the derivative of a log function. So again, remember from like your first calculus class, if you take the derivative of the log of something, you're basically multiplying 1 over whatever's the inside of the log times the derivative of the inside. Okay. With the student to teacher ratio, if we had log of the student to teacher ratio here, this would be 1 over the student to teacher ratio times the change in the student to teacher ratio. The change in the student to teacher ratio divided by the original student to teacher ratio, that's the percent change in the student to teacher ratio. Okay, I think I have it written out a little bit more implicitly here. So here we go. We changed the regression from just entering the student teacher ratio in level form. So before we had student teacher ratio in level form, that is just people. We can change it to log form by taking the natural log. So now if we want to get the partial effect with respect to the student-teacher ratio, we can again take the partial derivative of this whole equation with respect to student-to-teacher ratio, STR. Okay, that's this line here. It's now going to be the derivative of STR, of log of STR. That's 1 over STR times 1. Is that clear? So really there's like this additional 1 term there. You guys all see that? I'm not hearing anyone.
Yeah.
Yeah? Okay. Now, if we did that same trick we did before of multiplying the change over to the other side, we end up with this. The change in the total score is essentially the percent change in the student-to-teacher ratio multiplied by beta 1. Okay. This here, the change divided by the STR, or the change divided by the original value, this thing is really going to be like 0.01, right? Like a 1% change, this ratio is going to be 0.01. If you want it in percentages, you really have to multiply both sides by 100, which will then make the interpretation in terms of the percent change in the student-to-teacher ratio. But that requires then that you take the estimated beta 1 hat and just divide it by 100. Make sense?
Yeah.
Ami, are you trying to say something?
Sir. Hello, hi Sam.
Yeah.
Yeah, when you introduce the log function, you just took the log of the one explainable variable, the STR. Why didn't you take the log of the total score?
I could do that as well. So the version of the model that we're going to run right now is called a level log model. We're keeping our y variable at its original level. We're only changing our x variable to be in log form. It's a level log. What you're describing is a log model. We'll take the log of the dependent variable and a log of the independent variable. That'll basically give us the percent change in the student-to-teacher ratio. What's the percent change in the test results?
Yeah, exactly. Yeah. Okay.
You can do that as well, right? That's all your decision. So you're now entering the hat of, I'm an econometrician. I need to figure out how I want to specify my model. Ideally, you want to specify your model that makes the most intuitive sense. Okay, that's the way an economist should approach it. What's going to be the specification that gives me the best way of explaining what the hell is going on? Now, a statistician's perspective or a big data person's perspective is going to be entirely different. They're going to be transforming the data in certain ways in order to maximize something like the adjusted R-squared. Because as you vary the scaling of the data, you're actually going to have different degrees of predictability. You're going to get better at explaining the variation in the model.
Okay, thank you.
I have a question.
Sure.
One of the things that I've kind of heard previously is that when you have a dependent variable such as GDP, like, you know, or variables like that, or other economic variables, that it is recommended that you take the log to do that in order to normalize it, right? Is that kind of what we're trying to do here in a way with this?
That's exactly it. It's just a way of providing better interpretability. So it's hard to wrap your head around student-to-teacher ratio. I mean, yeah, it makes sense, right? Student to teachers. But at the same time, I'd rather just think about it in terms of percentages, right? As class sizes grow by 3%, what's the impact on test scores? Make sense? So it's just another way of restating the exact same problem. But the way you restate it is going to change the way you interpret the data. And it's going to be the way you interpret the model. And it's also going to rescale and change the way you interpret the coefficients as well. Make sense? So you can't just like change it as you see fit. I mean, you can, But as you do, you need to make sure that you're understanding how you interpret your model, because interpretation is going to change depending on the units of the data going in. Okay? So whenever you take the log of a variable going in, you're essentially trying to interpret it in terms of percent changes. And hopefully this derivative will explain to you why that is. Okay, so let's estimate that version of the model. We're going to create a new column called log str. So log str, we're just going to take log of the column inside of CA schools called str, the student-teacher ratio we made before. Okay, log here is natural log. Okay, now we're going to use the linear model again. Total score is going to be our independent variable, our dependent variable, and our independent variable is going to be log of the student-to-teacher ratio, again inside of the CA schools data set. If we run this model, we're going to see some slight differences. Our intercept is entirely different. Our beta 1 hat is entirely different. And it's because the scaling is different. Okay. Another thing, our R squared and our adjusted R squared are different than before. Okay. So on this version of the model, I think I can actually like mark up the screen here. You know what? I don't want to type with Zoom anymore. Okay. So here we're saying the estimated model is minus, or the beta 1 hat is minus 88.59. Okay. And the R squared is 0.05173. The adjusted R squared is 0.04946. Okay, jot that down. Adjusted R squared, 0.04946. If I scroll up, I can take a look at our model from before. The adjusted R squared before was 0.04897. By simply rescaling the data, our model actually has a slightly better fit. Okay. Now here, it's not really a big gain. Okay. Imagine you're working with data like income. There you're going to see huge differences. And the reason is a lot of people have incomes that are clustered around the median, right? So like then what's the median income in the United States? Come on, you're economists in a grad program. What's the median income in the US?
Like 36, right?
A little higher.
67.
A little lower.
1,000.
We'll call it 50, okay? The median income is about 50. It's about 52,000. There's a lot of people that have substantially higher incomes than that. There's a lot of people that have incomes in the millions. There's people that have income in the hundreds of millions in any given year, right? And there's a lot of people that have zero income. That sort of data is very lopsided. There's a small number of big outliers, and that data is going to look very skewed, or the distribution of it is going to be dispersed. It's going to be all over the place. By taking the natural log of that data, you're going to compress it. You're going to bring everything closer together, right? You guys know what a log function looks like? Yes? Okay. I think I can draw directly on my screen. Let's see if this works, right? So a log function looks something like that. Wow, that's cool. Okay, where that's my x-axis, that's my log of x. This is complicated, okay? As this tends to infinity, this is going to be diminishing. It's not, the second derivative is negative, so it's slowing down over time. Okay, so the first derivative is positive, it's always increasing. The second derivative is negative, so it's slowing down over time. The rate at which it's increasing is decreasing. Make sense? Okay, what that means is if there's an x that's like enormous, it's going to bring, the log function is going to bring it back down towards like 13 maybe, or 14 or some small number. Okay? Clear all my drawings. Go away. Yes, it worked. Okay. So if we look back at now at our log specification, the intercept term is entirely different. Before we had 1,397, now it's 1,571. Okay, who wants to interpret this for me? If there is a 1% increase in the student to teacher ratio, what is the impact on the test score? 1%.
Minus 0.88.
Sorry?
Minus 0.88.
Exactly. Okay. So we said before in our little derivation here, a 1% change is basically 0.01. So it'd be 0.01 multiplied by beta 1, which would be 0.88. Or you could think of it as a 1% change, divide the beta by 100. That's a 0.88% decrease in points. Okay. So what that means is if there is a 10% increase in the classroom size or a 10% increase in the student to teacher ratio, that's going to lead to a drop in 8 points. Okay. Whenever you're reporting your statistics and your research, you want to come up with a magnitude that makes sense, right? You don't want to say, oh yeah, a 1% change leads to a 0.8 unit drop in test score. You can, but when the data is that small, you're better off using a slightly bigger number. Like a 10% change in the student teacher ratio leads to an 8% drop, or an 8-point drop, not 8%. Make sense? Okay. So I believe down here, I've put in a link for you guys.
Hey, Hassan, before we move forward, are intercept changing? What does that mean? Like that intercept, we said that was the minimum score, right? Originally the 1397.
It's not the minimum score. It's the score holding constant it's your score conditional on all your x's being 0.
Oh, got it. Okay. So it's okay for it to be changed because now our terms have changed units.
Exactly. The scale of our x has changed.
Mm-hmm. Thank you.
Yeah.
Hasan?
Yeah.
If we can just take the natural log of something and adjust the units of measure and get a better fit, I mean, that's, God forbid, if you wanted to manipulate the data, you could do so doing that and make it look like your model is better than it is, right? I mean, if you just switch the units of measure, right?
Yeah.
Okay.
Yes, that's exactly it. So that is something you have to keep in mind, especially when you're reading papers. But the truth is, I mean, that sort of rescaling will have it's really a tiny effect. It's never going to be enormous. The only time it is enormous is when you're dealing with data that's like very skewed in some way, in which case you can't really do anything unless you actually take the log.
Gotcha.
Like if you're doing something like predicting house prices, house prices are all over the place, especially if you're dealing with like Southern California home prices. You have some areas where it's like $300,000 for a home. You have other areas where it's the median home price is $1 million or higher. Right, so that data becomes all over the place. By taking the natural log, you bring the distribution together. It looks a little bit more normally distributed. Then you can actually try and fit a line through it. Right, so usually it's not done to like manipulate. So it's not usually done with that intent. It's usually done with just to come up with a better model. But it can be.
But it's usually a marginal effect, you say?
Yeah, it's usually pretty tiny unless the data is just really lopsided, like going in. Okay. So here I have a little note for you guys. Whenever you have a regression model in R, you can use the predict function to basically plug in values into your estimated regression model, and it'll give you the predicted value. Okay. So I can predict the log model with some new data. The predict function expects you to pass in a data frame that has the variable names exactly as they appear inside of the regression. Okay. So if I wanted to predict, for instance, what's my predicted test score for a school that has a log student to teacher ratio or a student to teacher ratio of 20, so 20 students per teacher. That's telling me the predicted test score is 1,306. Okay, what if there's actually 21 students per teacher? Then it's saying there's actually 1,301 students, or 1,301 is a predicted test score. Okay, when you're dealing with logs, the difference between 21 and 21.1, the difference in logs is approximately equal to a percent change. So, sorry. Here I've written for you guys the difference between the prediction at 3 and 3.1. 3.1 is approximately 10% higher than 3 in logs. The predicted test score is 8 points different. So it's a 10% increase in the student to teacher ratio. Okay. Now, this is this link I was mentioning a little bit before. I want you guys to take this link and go to the site and like memorize these specifications. Okay, these are things you'll learn them over time, but having this table is super helpful early on, and they have some cool little tables showing you how to actually derive all the different specifications. So the first specification is basically what we've been dealing with. It's a level regression. You're keeping your original response variable, your dependent variable in its original form, and you're keeping your explanatory variable in its original form. The alternative is you could do a log level, where you take the natural log of your dependent variable, then it becomes a percent change in your y variable. Okay, and you can keep doing the same thing for different versions of it. This is typically the nicest specification you can run your regression as, because you're keeping everything in terms of elasticities. Everything's in terms of percentages. A percent change in x leads to a percent change in y. Right, so a blank percent increase in the student-teacher ratio corresponds to a blank percent change in the test scores. Okay, so I urge you guys to click on each of those to view these videos, and then click on each of these links, and they'll show you basically the derivatives and how to interpret each of the models. It's pretty good. Okay. So hopefully you have a pretty good idea now of interpretation. What we're going to do now is talk about some diagnostics, right? So cool, I ran a regression. I know how to interpret that regression, but I have no idea whatsoever if it's actually correct or not. Right? That's the truth. You can run a model and R will spit it out. It's never going to tell you, yes, this is right. You know that's wrong. Okay? Your job is to figure out, again, as an econometrician, what belongs inside of the model and what does not. You can't just decide, yes, this belongs, no, this doesn't belong. You have to have an actual logic or reason behind what belongs where, right? And this could be as simple as like some simple intuition, like, yeah, I should probably control for the percentage of people that actually speak English when trying to predict test scores, right? That may have an impact. Or I may want to control for things like income. That also may have an impact. Okay. There are formal ways for deriving models. The formal ways are called structural models. I'll upload a book for you guys onto Canvas from Stanford, or I forget who it was. It was a professor at Stanford. They wrote a book basically walking you through how to derive structural models in econometrics. Essentially, you write down a theoretical model, and from that theoretical model, you have these agents that are doing some optimization problem. From that optimization problem, you get some parameters, or you basically get a regression equation that falls out of the theoretical model, and then you go about estimating it based on what's in the theoretical model. Make sense? So basically, you write down some theory, the theory guides your specification, you get some data then to fit the specification. Okay. when we were deriving OLS, we actually made some assumptions about what can go into our model and what can't. Specifically, we made one strong assumption when we were solving our optimal solution for beta hat. We said we cannot have perfect multicollinearity among any of our explanatory variables. What does that mean?
That our explanatory variables are not perfectly related to one another.
Yeah, I can't have any one x variable that has a perfect linear combination of the other x variables, put simply. Okay. Now, the easiest way to see this actually is through categorical variables. Okay. A categorical variable, or more plainly, a dummy variable, is a way of representing categories inside of a regression. Okay. The way you can think of categorical variables is something like this. Let's say I want to control for cats and dogs. Okay. I'm dealing with some data and I want to control for cats and dogs inside of my model. Let's say I'm trying to predict something like the weight of an animal. So weight equals some beta 0 plus some beta 1 times species. This is painful. Okay, times species. Okay. I can't just write the word cat inside of a regression, right? I don't know how to invert a matrix that has the word cat in it. But what I can do is create a variable that represents the word cat. Okay, so species might be a variable that looks something like this. It might be a 1 if the species is cat. Thank God I chose 3-letter words. It might be a 0 for other species, all other species. Okay, so in this specification, I'm trying to predict the animal's weight, maybe in pounds or in ounces, based on some average weight plus some beta 1 times the species, which is a 1 if the species is a cat, 0 otherwise. Okay, so that's a way for me to take some words or some categories and code them up as an actual mathematical number. 1 if it's a cat, 0 if it's not a cat. Okay, this actually has a special interpretation then. Because if I want to predict the weight of an animal now, basically I'm going to predict the weight of every animal that's not a cat is going to be what? I have an animal that's not a cat. What's the predicted weight by this equation? So that's a beta 0 hat and that's a beta 1 hat.
Just the average, right?
Just beta 0.
Mm-hmm.
Okay. If my species is a cat, what's the weight?
Beta 0 plus.
Beta 0 plus beta 1 times the species, which is a 1 times a cat. The 1 is a cat. So it's beta 0 plus beta 1. So basically, whenever I have a categorical variable, what I'm doing is essentially fitting 2 different intercepts. I'm fitting one base intercept at beta 0, and then I'm going to shift that intercept up or down depending on the category. If it's a cat, I'm going to shift it, for instance, up or down. It's going to be a variable that changes relative to the average, relative to beta 0. So that would be beta 1 plus beta 0, for instance.
So would you call that a slope dummy? Right, that's what that is?
It's not a slope dummy.
Not a slope dummy.
No, a slope dummy would be an interaction.
Oh, okay.
Okay. So here it's just a variable that represents the category cat. Okay. Let's go through another example, going back to our data set here for schools. Okay. Inside of this data, we have this categorical variable, grades. It tells us which grades the school serves. There are 61 schools, so a table will tell us how frequently a categorical variable occurs. So it's telling us the variable KK06, kindergarten through grade 6, appears 61 times. KK through 08, kindergarten through grade 8, appears 359 times. So here I have really in my sample 2 different kinds of schools. Those that serve kindergarten through grade 6 and those that serve kindergarten through grade 8. Okay? I can create a dummy variable for this group, and I can create another dummy variable for this group. Okay? We'll create one variable called KK06, which is a 1 if this statement is true, 0 otherwise. Okay, so if else is a vectorized if statement. It's going to go through the grades column, and it's going to check for every single entry if this statement is true. Is the entry inside of grades equal to KK06? If it is, it's going to return a 1, otherwise it's going to return a 0. We're going to store that inside of KK_06.
Is there a way to automatically do this instead of us assigning it? So instead
Yes,
of, okay.
there is. It's called a factor variable, but we're not there yet. Okay, so you can actually automatically make all your dummy variables for you. But if we're going to continue this trajectory of making everything manually, we can have this second dummy variable that is a 1 if this variable, or if grades is equal to 08, 0 otherwise. Okay, so now I have 2 new columns. So if I preview the data set, there's 2 new columns. So this first school, KK06 is 0, KK08 is 1. Is it ever possible for a school to be in both categories?
The score should be in only one category.
There should only be one dummy. These two things basically say the same thing. If you're not in KK06, you're in KK08. If you're not in KK08, you're in KK06.
Exactly.
Right? I mean, here, when I ran table, it's basically summarizing the entire data set. It's telling me there's only these 2 categories. Yes? So really, these 2 columns we just made are inverses of one another. Whenever KK06 is a 0, KK08 is a 1. Whenever KK08 is a 1, KK06 is a 1. They flip. Did I say that right? Whenever KK08 is a 0, KK06 is a 1. Whenever KK06 is a 0, KK08 is a 1. It's the same information stored in 2 different columns. This is perfect multicollinearity. Or this is called a dummy trap. These 2 dummy variables represent the same information in slightly different ways. Okay. Now, if we were to run a regression, so here we go, linear model, total score. If we were to run a regression where we controlled for KK06 and KK08, both of them, we have perfect multicollinearity. We know that. If we run this regression, did we get any warning signs? No. Did we get any error messages? No. But if we look at the summary of log model, oops, I have the wrong variable name there. It should be log model with dummy. If we look at that, if we run that command, we're going to see this output here. You guys all see that? Were you able to run that?
Yes.
Okay. KK08 gets a coefficient of NA. It's missing, right? You guys all see that? KK08 is missing.
Mhm.
Okay. R is checking if your matrix has full rank before it solves for the optimal solution. It has to do that, otherwise it cannot invert the matrix. X prime X inverse. It can't invert X prime X if it has multicollinearity. Because of that, R is going to drop one of the columns. Usually the last one. Okay? Because the two columns have the same information. So this kind of helps us, right? So again, we're talking about model specification. Well, this kind of restricts one thing. I can't have the same thing twice. It makes my life a little bit easier, right? Okay. So I can remove KK08 from here and rerun my model. Nothing is going to change. Okay. How do I interpret this model?
I have a question.
Yeah.
Would you get the same thing? So would R be able to detect that you have perfect multicollinearity if you have a variable, let's say, if you have two variables that are the same, but the units are just different? So like
Yes.
inches and feet or whatever.
Yes. As long as it's a linear combination of the two, we'll be able to, it'll automatically drop the result for you.
Thank
Or
you.
it'll automatically drop one of them for you. Okay.
Thank you.
Sometimes it's annoying though, because it'll drop the wrong variable, like it'll drop the one that you want to actually interpret. Okay. Nonetheless, let's focus in on this really quick. We have the total score is equal to beta 0 plus beta 1 times log of STR plus beta 2 now times KK06. Right? That's our new model. Okay. Where KK06 is going to be a 1 if the school serves or if the school is up to 6, it's going to be a 0 otherwise. Otherwise really means in this case up to grade 8. Yeah? Make sense? Okay, so let's interpret this model then. We have beta 0 is estimated at 1554. Beta 1 is estimated at minus 83.46. And beta 2 is estimated at 15.19. Right? That's what these coefficients are estimated as. Sorry, is this too messy to understand?
It's fine, Hassan.
Okay, thank you. Okay, so if I wanted to figure out now the predicted score for a school that serves up to grade 8 and has a student to teacher ratio of 10, or a log student teacher ratio of 10, what is the predicted score? We'll have 1554
Plus
minus 83.46 times the log of 10 plus, I said serves up to grade 8, plus 15.19 multiplied by what?
0.
By 0. If the school serves up to grade 6, this would be a 1. Interesting. So ignoring all of this crap, or ignoring all of this term, if we were to ignore this for a moment, we're saying that if a school only serves up to grade 6, on average, their test scores go up by 15 points. Right? So we can ignore all of those terms. Ignore all else. On average, a school that serves up to grade 6 has 15 This is so complicated. Has 15.19 higher average test scores. This is interesting. Holding the student-to-teacher ratio constant, putting that aside for a moment, so we can compare two schools, same student-to-teacher ratio. If one school only serves up to grade 6, on average, it has higher scores. Remember how we were doing difference of means? We compared two groups, like a t-test? We're essentially doing the same thing. We're doing a t-test now, but it's partitioned. It's partitioned, holding constant a student-to-teacher ratio. Which ratio? Any of them. Okay, and we can tell, is that difference between the two categories statistically significant? Well, that's going to depend on the significance of beta 2. That's going to depend on this significance. What's the significance of 15.19? Okay. If we go back and I screen share my desktop, hopefully it doesn't go crazy again. Still working. We can see there actually is a statistically significant difference at the 5% level, or at the 1% level. 1% level, yeah. Okay. So there's two things I want you to take away from this. One, with dummy variables, we can run into a dummy trap. Okay. With dummies, you only want to include one category because one category basically includes the information of two categories. Okay, so you don't want to run into perfect multicollinearity with dummies. You can do the same thing with geography, by the way, right? So like, let's say I broke up California into 4 regions: north, west, south, east. I can't have a dummy for all. I can't include north, west, south, and east inside of my regression. I can only include 3 of them. Because if I include 4 of them, I'm going to have multicollinearity. Because if it's not one of the 3, it implies it's the other one. Okay? To show you an example of that, I mean, you can think of it like this. Let's see if I can just draw here in R. All right, so if I have north, west, south, east, if this is 0, that's 0, and that's 0, that necessitates that it must be north. That's a 1, right? If that's a 0, that's a 0, that's a 0, that means the school must be in the east. That's a 1. Okay? So you can only include any 3 of the categories. You have to leave one category out. Make sense? Otherwise, you're going to have multicollinearity. Okay. So that's the extreme case. That's the case where I have perfect multicollinearity. My matrix doesn't become full rank anymore. I can't take the inverse, so I have to drop one variable. Okay? That's kind of an obvious case. What about the not so obvious case? What about the case of I have omitted variables? I chose to leave some variable out of my model. What does that do? Well, we can actually solve for it. When we're choosing to omit a variable from our model, it's basically like we're just tossing it in the residual term. We're just forgetting about it. We're letting it reside inside of the error term. Okay. I'm going to try and jump back onto the iPad. Okay, so imagine this. We now know our optimal solution for ordinary least squares, right? We all have it tattooed. Beta hat equals x prime x inverse x prime y. Yes? Actually, 1 second. Let's try this again in Zoom. Okay, so that's our optimal solution for ordinary least squares, right? We said this was the optimal solution under the condition that our true model was y equals x beta plus epsilon, right? That was the true model we specified. Okay. If we have a case of omitted variable bias, that is, this isn't actually the true relationship of y. This isn't the population version of y. Let's say the population version of y actually had some additional stuff in it. It's y equals x beta, the stuff we observe, for instance, plus z times gamma plus omega. So our new residual term is omega. There's this new set of variables, z, and a new set of weights, gamma, that we didn't control for. We decided to leave it out of our model. Okay, so z we're going to call omitted. Okay. If this is the true version of y, then if we were to plug in that true version of y into what we estimate, we can actually see if there's anything wrong with our model. So we can go back to beta hat. We'll still have our x prime, x inverse, x prime. Now we can plug in for what y actually is, the true y. The true y is x beta plus z times gamma plus omega. That's the true y. If we distribute this term out, we're going to have beta hat equals x prime, x inverse, x prime multiplied by x beta plus x prime, x inverse, x prime, x inverse z times gamma, so x prime, plus x prime, x inverse, x prime, omega. Right, just pass through this entire term, just distribute this out. Yes? Okay. Now, if we were to take the well, actually, first off, there's one thing that's dead obvious. Here I have x prime x inverse multiplied by x prime x. What's the inverse of something times itself?
The identity matrix?
It's the identity. So this thing is just going to become beta hat equals beta. Identity is basically 1. This term is going to stay the same. X prime x inverse x prime z times gamma plus x prime x inverse x prime omega. Now, if we condition beta hat on the sample we observe, on the X data we actually observe, we can take the expectation of beta hat conditional on X that's going to be beta. Beta is the population parameter. It's itself. It's a constant. It's a number. This term is basically just a number, this X prime X inverse thing. So we're going to have X prime X inversed multiplied by the expectation of X prime Z conditional on X times gamma. Gamma is just a number. Plus the expectation of, plus we can pull out that constant term, X prime X inverse, the expectation of X prime omega conditional on X. Can you guys all see that? Okay. If we assume, like we did in the Gauss-Markov assumptions, that the error term is totally uncorrelated with our X's, this term is going to go to 0. Because the expectation of the residuals is going to be 0, right? The expectation of this thing is going to equal 0. So if I assume that X and W are independent, I can break up those two terms from one another, and then it's going to multiply by the expectation of 0 because I have an intercept. So this whole term will 0 out. So what I'm left with then is the expectation of beta hat conditional on X is going to be beta plus this term. That term I'm going to call my bias. If my estimate, which we proved in class together, was unbiased, when I take the expectation of beta hat conditional on X, it should just be beta. But because I have this omitted variable, Z, from my specification, I'm actually injecting bias into my model. The degree of the bias is going to be governed by how strongly X and Z are correlated or related to one another. That is, if there's something that's very correlated with one of the variables I'm actually controlling for that I left out, that's going to bias all of my estimates by a lot. Okay? In absolute terms, this is going to make all of my coefficients bigger. It's going to make them bigger by the amount of the bias in absolute terms. Right? So if I added an absolute value to both sides. Does that make sense? Okay. Going back to our little example here. So far, we just ran a very simple regression. All we did was total score is beta 0 plus beta 1 times the log of the student to teacher ratio plus epsilon. Do we think that everything that explains the total score on average for a school is purely driven by just the student to teacher ratio? No, we're not that naive, right? There's lots of other things that matter. Okay? That means we're omitting lots of variables from our model. Some of those variables could be very strongly correlated with the student to teacher ratio. Because of that, our estimate here for beta 1 hat is in fact going to include a large bias term. Okay, let's see an example of that. Let's just add in an additional variable. So let's add in an additional variable. The variable we're going to add in is the proportion of students that speak English at the school. Okay, so first thing we can check is, well, what's the simple correlation between English and the student to teacher ratio? The log of the student teacher ratio, a variable we chose to leave out. We chose to leave out English, right? The correlation is 0.2. Is that a lot? Well, we can compare that correlation to the correlation we measured, which was the correlation between total score and the log student to teacher ratio. That correlation was -22. Okay, so they're both strong, relatively strong correlations to one another in absolute terms, but this one is strong in negative and this one is strong in positive. Okay, so there's a variable that we know is omitted, the proportion of English speakers. We omitted it, and it's correlated to the log to student to teacher ratio. Because of that, we're basically saying English is being unexplained variation inside the residual term. If we were to include that inside of the model, we'd be moving it out of the residual term, out of the error term, and actually into the model. By doing that, we're going to take away some of that bias. Okay, so if we rerun our regression now, linear model, regressing, total score on log of STR plus English, so we're adding on now a second independent variable. We can take a look at our new model. The coefficient size on log of student to teacher ratio before was, what was it?
I think it was 88.
It was 88, now it's 42. That's huge, we cut the magnitude in half. By simply bringing in one additional covariate. Okay, so properly specifying your model is extremely important. If you leave something out that really matters, that is correlated with one of your independent variables, if you leave it inside of the residual term, you're going to have huge omitted variable bias. Okay, now, I've been working on putting together a data set for you guys, which is going to be for your homework this week. The data set is COVID data, but I've taken the COVID data and I've set it up so I made it really clean for you guys. So it's basically just going to be total number of cases is your dependent variable. That's what you're going to be trying to predict. And you're going to be explaining it based on a bunch of variables that I've added on at the county level. Things like income, things like unemployment, things like population density at the county level. Okay, I'm going to give you guys that data set for your homework. I want you guys to toy around with the data and try a bunch of different specifications to see what is predictive of the number of cases a county has. Okay, I'm bringing that up because we only have like 10 minutes technically left in class. So rather than jumping into.
And are you looking for the IVs, which are the most predictive, or just the number 1, number 2, 3, 4?
Okay, so I know it's nice to use acronyms like IVs, like independent variables as IVs. In econometrics, don't use IVs for independent.
Okay.
Because IVs actually has a very specific term inside of the language of econometricians, which is instrumental variable. So you don't want to call it an IV.
Gotcha. Okay.
Okay. I'm going to leave that to you guys to decide what do you think is important.
Okay.
Okay. I want you guys to toy around with the model and to practice some data handling skills, especially this data set, because it's, I mean, I'm going to give you guys also things like how long, like when how many days it's been since the first case appeared inside of that county. So you'll be able to even include things like time trends. Okay. The last thing I want to cover today is a way for you guys to visualize heteroskedasticity. It's actually very, very straightforward. So I've described this idea to you guys verbally, and I think we did in class together, like it was the last thing we covered before all this pandemic stuff. But basically, you need to decide. So here we just showed by adding in an additional covariate, we've cut the size of this coefficient literally in half, right? So student to teacher ratio doesn't seem all that important anymore. Okay, why do I say it's not important? Statistically, it's still very significant. Okay, I'm saying it's statistically significant from 0. However, I'm saying it's statistically significant using the Gauss-Markov assumptions. I'm imposing that there's homoscedasticity among these residuals. That is, all of the errors are not appearing in any systematic way. Okay? We can actually visualize and test for homoscedasticity. Okay. This is also going to be part of your homework assignment. I'm going to give you guys a formal test. There's 2 tests you can actually run, statistical tests, to determine if there's homoscedasticity in the residual term. One is called a White test, and another one's called a Bruch-Pagan test. So I'm going to show you guys how to do that in the homework assignment. But the easier thing to do, the much easier thing to do, is literally just plot out the residuals. Okay, so that's what's going on in this next 3 or 4 lines of code. Okay. If we want to get the fitted values, the y-hats for our estimated model with English, we'll call that y-hat. We can extract the residuals from the model as well using $sign residuals, so grabbing one of the elements of the list that R returns. We can plot y-hat, the predicted values of y, along our x-axis, and we can plot the residuals along the y-axis. Okay. You'll get a graph that looks like this. Okay. With homoscedasticity, you should be getting constant variance. You should be seeing basically the variance is all kind of fixed. Okay, it's all within a certain range. The errors are not systematically higher in one region or another region. Okay. Here we have, again, predicted test score. That's what's on the y-axis. Oh, sorry, the residuals is on the y-axis. The predicted test score is on the x-axis. Basically what we're seeing here visually is as the predicted test score increases, the errors are increasing. You guys see that? It's kind of this like trend where in absolute terms, the error is just growing, right? Okay. That's a clear sign that it's not homoscedasticity. The variance isn't constant. Okay. An even better way to really plot this out is instead of plotting the residuals, you can just plot the absolute value of the residuals or the square of the residuals, which basically is their variance, right? And you'll see something that looks like that. As we get into the domain of higher predictions, we're making more and more errors. The errors are getting bigger. You guys all see that? Okay. This pattern is a clear sign that we do not have constant variance. Okay. Constant variance would look like this. It'd be like a bunch of dots basically along a line. The fact that we see this clear systematic pattern, this is a sign of heteroscedasticity.
So if we were to use a robust estimator, we will get a greater standard error?
Yes, it's going to inflate the standard errors to correct for that. Okay, so we can do that. Whoa, go away. All right, cool. I got to live with that on my screen now. Annotate, clear, not save, clear all drawings. There we go. Okay, so again, now that we've implemented the sandwich estimator with the white estimate of the variance covariance matrix, the robust version, we can just use the basic package in R, the sandwich package in R, to just use the built-in function to derive the standard errors for us, the corrected versions. Okay, the original standard errors were here. Minus 2.869 was the standard error for log of the student to teacher ratio. The new corrected standard error is minus 2.42. The p-value, though, is larger than before. Right, so sorry, that was the t-statistic. The p-value, the standard error is 17.41. The original was 14. Okay, so using the sandwich estimator, after checking for heteroscedasticity, we can show that the standard errors do in fact inflate. They do get bigger when we allow for variation in the residuals to be different from one another. And that's where we get this version for significance testing. Okay.
What was the second plot that you did? Was it the R squared, the residual squared?
The residual squared. The residual squared is essentially that variance covariance matrix.
Oh.
Right? Because we said before, the variance covariance matrix essentially just looks like what's going inside the variance covariance matrix is like epsilon 1 squared, epsilon 2, fuck, that's awful, epsilon 2 squared, all the way down to epsilon n squared, right? That's on the diagonal, which is basically the residual squared. Not basically, it is the residual squared.
Got it.
Make sense? So again, under the Gauss-Markov assumptions, we're assuming that all of those residual square terms are the same. Clearly, when we actually plot out the data, that's not the case. Right? Here's the square of the residuals. As we plot them out over time, they're varying, they're growing. Not over time. Over the predicted values, they're growing. Okay. When you're dealing with time series data, you do plot out the residuals over time, and there you check for no autocorrelation. That is, you want to make sure your past residuals are not predictive of future residuals. There's no serial dependence. And that's what time series is basically focused on entirely. Okay. So we're going to spend next week going through collecting data on the internet. So we're going to spend some time doing web scraping stuff. But I urge you guys to flip through the lecture I've already uploaded. It's already there for you. Okay. I really want you guys to get in the habit. I want you guys to leave this class like feeling like you can get data from anywhere.
But Hassan, what does this mean about our model? Does it mean that our model is not complete because as the errors are increasing? Like, what does it mean?
No. All it implies is we need to use a robust estimator for the
Okay.
variance covariance matrix of the residuals, which is what's done next in the next bit of code.
Okay, so it doesn't mean the model is not right. It's just we need to use a different estimator for this kind of data. Okay.
We need to just do a different estimator on the residuals. We need to use the robust sandwich estimator in order to come up with, or in order to properly do statistical inference.
Okay.
That's all. Right? The whole idea of, is my model properly specified? There are tests for that, okay? One of them, for instance, is there's something called the Ramsey reset test. For those of you that are reading the Woolridge book and actually following along, right? The Ramsey reset test will basically do a specification test. It'll tell you, should your model include like a log form of a variable instead of a level form? Okay, so hopefully on the assignment, which I'm going to post probably tomorrow, you'll have access to this sort of stuff. But you'll be able to experiment with these sort of tests. Okay. So again, today was kind of just like a, let's take a step back from the math and let's actually interpret everything and understand what everything means. Good?
Good.
Okay, any questions? No? Okay. As a reminder, we are still doing office hours. So I know a bunch of you guys jumped on the Zoom call last week. That was fun. So if you have any questions, feel free to jump on the Zoom call on Wednesday as well.
Same time?
Same time as last week.
Thank you, Doctor.
All righty. All right. Take care, everyone.
Thank you.